Hi, my name is Andre Workington, and this will be a brief update on ARM-based infrastructure and workloads with VMware. First, a brief disclaimer. This is a purely informational presentation. Uh, Features are subject to change. Don't make any contracts based on what you hear today. This is VMware's value, multi-arch for maximum flexibility and use case alignment. From the cloud all the way to the edge, we expect ARM-based infrastructure and workloads to be proliferating outside of the traditional enterprise computing rules, and successful adoption implies a CPU and scale-agnostic infrastructure with no silos. Last year, you may remember VMware launching Project Monterey, a paradigm shift in the way traditional server infrastructure is implemented and deployed by our customers, employing ARM-based SmartNICs to offload networking and storage functions for maximum flexibility, performance, and security. Project Monterey represents the first real productization of the ESXi-Arm incubation work over the years. Last year, we also finally put out a no strings attached evaluation of the ESXi on ARM technology that anyone can try on systems ranging from a diminutive Raspberry Pi to rackable servers, all to better understand the drive and demand for a virtualization based product in the market. This year, we've announced a tech preview of VMware Fusion on Apple Silicon, enabling our customers with new Apple Silicon Macs to continue using the much loved VMware Fusion product for their productivity and development needs. Fusion on Apple Silicon represents the second real productization of the ARM virtualization enablement work at VMware, and the tech preview is available today. Go get it. Over the years, we've done much to enable ARM based infrastructure and workloads, growing support for ARM across critical pieces of our software stack, including the ESXi hypervisor, the vSAN enterprise grade storage virtualization software, and NSX, the networking and security virtualization platform. Our port of the ESXi hypervisor to the 64-bit ARM architecture runs on standards-based systems across a wide range of footprints and use cases, and runs most of the off-the-shelf OSs that matter in the market. We've also been working closely with ARM and our partners to help shape the system-ready hardware and firmware standards to unlock the most value. You've already seen some of the key pieces through the ESXi-Arm Fling and now Fusion on Apple Silicon Tech Preview. The capability and the standards work has also led to Project Monterey, which is still in development. But we're not stopping there. We are exploring further areas where ARM can make a difference for VMware and our customers. Because the end goal is to have operational consistency between all supported architectures and environments with no silos. So now, for something really cool, let's talk about the tech preview of VMware Fusion on Apple Silicon. Fusion on Apple Silicon presents a familiar environment to run supported operating systems that comply with the ARM system-ready specifications. As you can see, this is a pretty comprehensive list and should be familiar to those already checking out the ESXi on ARM Fling. There are no binary translation shenanigans going on, so x86 virtual machines are not supported. This is a very familiar experience to anyone running Fusion on a Mac. Here you can see a pretty standard Ubuntu installation, and as you can glean from the VM list, quite a few other operating systems work as well. The usual VM tricks like snapshots and suspend resume work as expected. You can see the 5.14 version of the kernel here, which has our graphics driver, as well as the 11.3 version of VM tools, which is built from source. So of course, you can use tricks like the host guest file system to access host shared folders. Here you can see 7 VMs running on an Apple Silicon Mac with 16 gigabytes of memory installed. So what works today? Today you can install Linux and BSD VMs from an ISO. You can control them with VMrun or the GUI. The big difference from the ESXi and ARM Fling is that we do have a 2D graphics driver now. And this is part of both an updated Linux kernel and BSD. So you need the newer VMware tools and, of course, 5.14 RC5 for Linux. The usual set of Fusion functionality like snapshots, clones, and virtual networking, that all works. And you can continue using Fusion to connect to remote ESXi or vCenter servers. And this should work with the ESXi on ARM Fling instances as well. The work on 3D graphics, that's still to do. Wayland support, if you wanted to use OVF tool or the REST API or anything with Kubernetes. So yeah, that's not supported. Probably the biggest, of course, gap today is support for Mac OS or Windows guests. Mac OS, of course, would require some fairly significant changes to be able to use it. And Windows support, of course, is heavily dependent on Microsoft choosing to support Windows on ARM with third-party hypervisors. So check it out. Go to vmware.com/go/get Fusion TP and download the tech preview of Fusion for Apple Silicon. Sign up with our forums. We want to hear back from you. Please leave your comments, requests, bug reports. We hope you really enjoy this tech preview. And now for a short demo.
So just to confirm and show folks here, I'm using a MacBook Air. This has the 16 gigs of system memory and 8 GPU and 8 CPU cores. So we're firing up an Ubuntu 2110 virtual machine. And to be clear, this is all happening in real time. So we've got the 5.14 kernel, which has our graphics drivers in it, as well as the 11.3 version of VMware Tools, which I built from source. We're taking a look at the CD or the mount folder, inside of which is our host guest file system. So our shared folders are exposed through this directory. And we can see that we've got my mic folder, my home folder added there. We're just going to add another folder there called dev. We'll back out of that folder and go back into it. And you can see there we have our dev folder and the contents of it. So clear out of that. And of course, likewise, if you view it inside of the file browser, you can see that if we go over to mount HGFS, we've got the two folders that we added there. So let's take a look at this performance of suspend and resume here. You can see that it's pretty quick. Suspending and resuming, in this case, a VM that has 8 gigabytes of RAM and 4 CPUs is pretty quick. So let's tax this a little bit and see what we can do to sort of push it. We resumed another Ubuntu installation. We're going to go ahead and actually install another operating system while we're exploring the other operating systems that are already installed here. So we're going to take a Photon 4 image and we'll go through this real quick. We're going to customize the settings a little bit. All of the VMs that I'm showing you here today have 4 CPUs and 8 gigs of RAM. So we're just going to go ahead and align that here. And we're going to increase the disk size. This isn't really necessary. It's just sort of my behavior when I'm installing operating systems to be consistent. So 1 Ubuntu, 2 Ubuntu. This one wants a software update. Let's go ahead and pull this out, take it into a full screen window, and let that software update go. And while that's happening, we'll go forward on the Photon installation here. I did skip over the password there, but everything else is in real time. Meanwhile, our other Ubuntu installation is working just fine. Let's bring up a quick video and just scroll through to give it an estimation of the performance that one can expect here. Keyboard shortcuts working just fine. Okay, let's see how our installation is doing. Oh, look, it installed in 16 seconds. Great. So while that reboots, let's get crazy. I'm going to power on, let's say 9 VMs here. We got Ubuntu 2004, Debian 11, FreeBSD 13, Fedora 34, which 34 should be updated to more current than that, just via the in-app updater. We have a Kali, one of the daily builds. So yeah, just sort of bouncing between them. Here's FreeBSD. Taking a look at the version of tools, which was built from the ports tree. Fedora 34 and 35, they actually ship with a newer version of the kernel and OpenVM tools, so we can right off the bat, without having to do much, go ahead and do things like change the resolution here. It's one of the features that VMware Tools provides. We have a Kali installation using an older version of the Linux kernel, so that doesn't do things like set the resolution and some of the other VMware Tools specific features. But Tools itself can be installed, just not the graphics drivers. Meanwhile, our other two Ubuntu virtual machines are performing just fine. Our Debian 11 has come up here. We can quickly just bring up a browser and show that this is all happening. And likewise with Kali, let's bring up a browser. So we've got 1, 2, 3, 4, 5, 6, 7, 8 virtual machines. So there you have it. You've got VMware Fusion on Apple Silicon running at least 8 virtual machines all at the same time. All these virtual machines are ARM. We're not doing any x86 emulation. This is all happening mostly real time. I cut out a couple of pieces here and there just to get through things like password selection, but otherwise, this is what one can expect when using VMware Fusion on Apple Silicon devices. Thanks for watching.
And now let's talk about Project Monterey. What we see is that new applications are using more and more of server CPU cycles. Now, traditionally, the industry has relied on the CPU for everything: application business logic, processing network packets, specialized work such as 3D modeling, and more. But as application requirements for compute have continued to grow, hardware accelerators, including GPUs, FPGAs, specialized NICs, have been developed for processing workloads that could be offloaded from the CPU. By leveraging such accelerators, organizations can improve performance for the offloaded activities and free up CPU cycles for core application processing work. On top of all of this, security risks are continuing to proliferate, especially with applications that are distributed across many locations, shattering the traditional perimeter security model. Security now needs to be distributed broadly, yet enforced locally. Doing that requires the proper hardware enforcement of those security policies and boundaries. The goal for many organizations is to get a zero trust security model. Rather than load up CPUs with this new security workload demand, offload accelerators can help solve this new demand for distributed security. These changes in workloads and security demands make the performance and efficiency benefits of hardware accelerators very attractive. However, these new hardware accelerators can create their own challenges. Adding accelerators to every host increases CapEx, while limiting accelerators to just some hosts increases OpEx. In the second model, operation complexity creeps up because IT operations teams need to figure out how to make sure the right applications are running in the right hosts with the right accelerators, and that there is enough capacity to run the applications with adequate performance. There is massive operational overhead that makes it harder for the applications to take advantage of these accelerators. So we see traditional infrastructure approaches are just not scaling and are not keeping up with the times. Project Monterey reimagines virtual infrastructure by extending it into a distributed control fabric that tightly integrates with DPUs, or data processing units. This provides a single secure operating model that unifies management for traditional, cloud-native, and bare metal workloads. This provides best price performance by offloading infrastructure functions from CPUs to data processing units and providing more CPU resources to applications. And this provides support for an enhanced zero trust security model by further isolating the workload domain from the infrastructure domain. Now, what's great is that Project Monterey preserves the existing day zero, day one, and day two experience that customers are familiar with. Project Monterey will support a broad ecosystem by bringing together DPUs from leading silicon vendors such as NVIDIA, Intel, and Pensando, and server designs from OEMs such as Dell, HP, and Lenovo. Here you can see the change in the server and software architecture as we replace the traditional performance NIC with a DPU. Now, you can provide the same infrastructure services to both virtualized and bare metal workloads, but with more security and with less overhead. Now, let's talk about some of the innovations in manageability, security, and performance. How will Project Monterey simplify infrastructure and workload management? Well, by managing the lifecycle of a DPU within vSphere, by enhancing observability into network operations through flow analysis and topology views, by managing the lifecycle of bare metal instances within vSphere. And how will Project Monterey boost infrastructure security with an enhanced zero trust security model? It will do so by isolating service provider and tenant infrastructure domains, and by extending microsegmentation to bare metal workloads. And how will Project Monterey improve infrastructure performance? And it will do so by accelerating infrastructure functions on the DPU. For example, for network, by handing off switching and routing. For storage, you could hand off NVMe over TCP, so basically DPU as the HBA. While for security, you could hand off the distributed firewall, IDS, IPS, the URL filtering, flood protection, and encryption. This all lets you achieve a higher workload consolidation and, of course, lower your TCO. Project Monterey is inherently an open ecosystem strategy. We are working with the leading SmartNIC vendors such as NVIDIA, Pensando, and Intel. Of course, you may be wondering why the Raspberry Pi is on the slide. You see, our ability to put our DPU operating system ESXi on this new class of ARM-powered devices hinges on industry standards around hardware and firmware. None of this would have been possible without the massive joint push to bring system-ready ES, or embedded server band of the specs, to the global community. We see system-ready ES as a pillar for enabling adoption of SmartNIC-based infrastructure. Standards help everyone get products quicker to the market. And beyond basic OS boot, we are working with partners to define SmartNIC-specific standards, including standardizing how DPUs are actually integrated into server systems. Now let's quickly turn to the ESXi-Arm Fling. The Fling has now been out for a year. This is a no-strings evaluation of our ESXi-Arm technology. We put it out there to learn more about the market demand for ESXi and ARM, to learn how people want to use it, and it's seen a massive amount of interest. Over 37,000 downloads, launching it to be the second most popular Fling of all time. Wow, thanks for that. We have been updating it periodically with fixes and new support for hardware and software. We launched the Fling on just a few platforms. The most crucial of these has been the Raspberry Pi, as it is the most approachable, cost and volume-wise, way to try out ESXi-Arm. And in fact, the work on Raspberry Pi firmware led to the creation of the system-ready ES band of standards that I just talked about. We also launched with support for two NXP Layerscape-based systems. One of these, the Honeycomb, is a microserver or workstation class system, while the 1046A four-way system represented an IoT edge gateway use case. We also launched with support for the Ampere Computing Emacs server. Folks in the VMware user community have done some pretty amazing things. We were thrilled to learn that ESXi-Arm was fundamental to improving the 64-bit ARM port of FreeBSD. We were awestruck to see live migration of RoboBrains. And yes, even though it's not something we support, folks have even managed to get Windows 11 for ARM booting in a VM. Wow. We have been also serious about soliciting feedback from the wider community and have acted on bug reports and suggestions, leading to various improvements to performance, features, and stability. Also, a few new hires to the team, and we've increased the list of hardware folks can try. We now support the official NXP Layerscape LS1046A based reference design board, as well as the all-in-one Raspberry Pi 400 PC. We've also added experimental support for the NVIDIA Caramel-based Tegra Xavier developer kits. If you have one of these, they are a pretty good value. It would have been fantastic to tell you that GPU virtualization is available, but alas, no. Sorry. But we do see a real value for these kinds of machine learning platforms at the edge. We've also extended support for the Marvell Armada A8040 based solid-run Macchiato bin and the newer Octeon TX2 CN9132 evaluation platform from SolidRun. And we've added support for the Socionex Syncquacer developer box if you have one of these crazy 24 Cortex A53 beasts. It's a unique and interesting low-power platform for edge compute. Finally, we've been busy adding support for the Neoverse N1 microarchitecture, which is ARM's own implementation of a data center-grade ARM CPU. We started with adding support for ARM's own development box, the N1 SDP, which ultimately led to adding support for the Ampere Computing Ultra-based server systems, including experimental support for the dual-socket Ultras. Ampere Computing Ultra-based systems are the default choice for anyone looking for an ARM server system this year. So this is a good segue to a new topic, ARM in the cloud. With some of the earlier ARM server design wins, one really had to shop around for workloads that would be a good fit. Usually, these were I/O bound. Now, the new Neoverse N1 based systems, like the ones based on the AWS Graviton 2 and Ampere Computing Ultra CPUs, are a real game changer that can chomp through all kinds of compute intensive tasks. We believe customers will want to run ARM workloads alongside their existing x86 workloads and leverage this flexibility in a multi-cloud environment. And yes, we have been looking internally at what ESXi could look like on top of an AWS Graviton 2 system. Here, you can see a vCenter managing a few shiny new M6GD metal systems and running VMs. Does this sound interesting to you? Let us know. What I am happy to share with you today is that because the Fling supports Ampere Computing Ultra CPUs, you can run the ESXi and ARM Fling on Oracle Cloud Infrastructure's new A1 bare metal shapes. These are dual socket systems, so support is experimental. Please see the extensive Fling instructions, special to the OCI environment, on directions for how to get going. And that concludes our presentation. Thank you very much.